Hello, this is Miss Salter, and this video is on our orbital motion problem from part 2. This is practice problem number 1. It's about a satellite over Mars, and we are trying to find the speed and the period of this satellite. So there was a fair number of troubles with this one, and I think it's because a lot of people didn't understand that there were subscripts in the uh, equation rather than squares or cubes, and so a lot of people were squaring things in the equation that didn't need to be squared, and then that messed up everyone's results. So let's go over this problem and see if we can clarify some things. So first off, we're given two different variables to start with. We're given the mass of Mars, so Mars mass is 6.42 times 10 to the 23rd kilograms. And we're also given the orbital radius, which is our R value, and that's 2.04 times 10 to the 7th meters. Now, you have to make sure that the orbital radius that you're given, this one is from the center of the planet to the satellite. If you're given a radius, like a distance that's from the surface of the planet to the satellite, then you should also have the distance from the center of the planet to the surface of the planet. And we did have one of our examples, the example from CK12 from Mercury, had that where you had to add up those two distances to get your entire orbital radius. This orbital radius, on the other hand, is already from the center of the Earth, center of the planet, Mars, to the satellite, and so we just need to use this number here. So these are our two givens. As I said, we're trying to find the speed and the period of the satellite. So let's start with speed. Speed is going to be v equals the square root of g times the mass of Mercury over r. Now, this is where we had the trouble. A lot of people had trouble with this. This part right here. On the example, it had M2. And what a lot of people did was they read M2 and said, oh, guess what? I have to square this. And then they were squaring the masses, and that was really taking their result to a whole another level. So this is just a subscript that describes what the mass is, because if you go back to the original equation had two masses in it. It had the mass of the satellite and the mass of the planet. But because of the way we can cancel things out, we didn't need to have that mass of the satellite anymore. We only needed the mass of the planet. And so because of that, we still keep the subscript, but that's why it's here, is because it's just telling us the mass of the object we're actually looking at. Not the satellite, but the planet. So we have G equals mass of Mars over R. So that is going to then be square root of, and there's lots of numbers here. So our G value is the 6.67 times 10 to the negative 11th. And then we multiply that times the mass of our planet, 6.42 times 10 to the 23rd, over our orbital radius, which is 2.04 times 10 to the 7th. And so when we do this now, this is the thing that helps me out when I'm doing this, is instead of just plugging this whole thing into my calculator and getting this big nasty number out, what I try to do is write down each of these math things, because then I can see what I've done wrong, and someone looking at my work can also follow along better in case you have a problem with plugging things into the calculator. Especially if you're using a calculator that doesn't have a scientific notation, the EE button. This makes it really difficult if you aren't sure what you're doing wrong to try to figure it out. So when I do this math, I get 4.282 times 10 to the 13th over my 2.04 times 10 to the 7th. And then when I divide that, I then get 2.099 times 10 to the 6th. And then, hold on a second, let me move this up. And then that equals then 1448 point. Oh, that's awful. Hang on. I don't like that either. 1448.8 meters per second equals my V, and I box my answer because it just makes it so much easier to find later on. So that was the big problem that most people seem to have. If it wasn't a math error and entering it into their calculator, it was that they thought that the subscript was actually a square and then squared that mass, and so that was a problem there. All right, next thing. So that's the speed. So now we're gonna go with the period. This one is a little bit more tricky. So period, we're gonna use. Oh nope, stop it. T equals. And then this one is just ugly, but it's okay. 4 times pi squared times r cubed over g times the mass of Mercury. Mass of Mercury, subscript, and then this too I think had a lot of trouble with just making sure that people were entering this into their calculator correctly. Okay, so we've got lots of numbers here. So we're going to go with 4 times 3.1415 squared times, and then I just put it in parentheses so I can keep track of it, and I know I'm entering it in my calculator correctly. 2.4 times 10 to the 7th cubed, all over 6.67 times 10 to the negative 11th times 6.42 times 10 to the 23rd equals. And like I said, I get really particular about making sure that I am working all of this math out step by step so that if I have a problem, I can find that problem quickly and waste less time in the long run later on. So what I did here was I did this part first, and then I also did the math for this part down here. And and I did do this, I did do the cube too. So then I did this cube part here. So that would be, let's make this pretty because might as well. So we got our square root, and then we have the red value, which is going to be 39.476. And then I'm going to times that by the green value, which is my cube. I'm going to times that by 8.4697. And I usually go out like 3 or 4 decimal places just to make sure that I'm getting as much precision as I can. Now, obviously, if we were doing this in a lab setting, it would be a little bit different. And then the blue one is 4.2. No point. 4.282 times 10 to the 13th. And then when we go back to combining these values, you get 3.3514 times 10 to the 23rd on the top. We still have the 4.282 times 10 to the 13th on the bottom. And let me move this up. And then therefore we divide those two. So then we get 7.8267 times 10 to the 9th. And then we do the square root of that, and we get 88,468 seconds. Or some of you then transferred that to hours, 24.57 hours. I took either answer. So there is this problem worked out for you, and I hope that helped you understand this type of orbital motion problem. Have a good day.